Hello everyone, very welcome to another session for thermodynamics subject. In this session we are going to start a new discussion about a new law of thermodynamics. Actually not the new law of thermodynamics generally, but new for you. In this session we will start to discuss about the second law of thermodynamics. First of all, let's see what you have learned up to now. And moreover, I should tell you about the content of this chapter, which is in close relation with the content for next chapter, which is about entropy. In this chapter, I will introduce you the second law of thermodynamics. We will see some the definition of that and also why it is an important law in thermodynamics. In next session, we will discuss about in the next chapter. Actually, we will discuss about the entropy, which is in close relation with the second law of thermodynamics. Up to here, in last two chapters especially, I've introduced you the first law, and we have seen the application and of these law for closed and open systems. The first law actually was about the energy conservation and uh, generally that this law actually the first law says that energy cannot be created or destroyed during any process. It can be just converted from another type to the other type of the energy, or from work to energy and vice versa. In this session, we will start to introduce second law of thermodynamics. We will see how this law help us to see to predict the direction of the process actually, and why a process happen in one direction and not in the opposite direction actually. And also we will see why a process is happening, why what are the conditions which a process can happen by those if have those conditions. And we will see some definitions concept related to uh, this law, like thermal energy reservoirs. We will see what are reversible and non-reversible processes. I will introduce you heat engines, refrigerators, and heat pumps, and we will see the process, and you will see how is the second law of thermodynamics for this equipment or devices actually. I will introduce you perpetual motion machines, and we'll see if we can have such a machine or not generally. And also I will introduce you thermodynamics temperature scale. And at the end of this chapter, I will introduce you Carnot cycle, which is the idealized cycle actually, which by this cycle we can get the most possible efficiency from a cycle during different processes. So let's start with some examples. You can see also here some objective of this chapter. These objectives are according to the outline which I mentioned in previous slide. Let's see with some examples what is this second law of thermodynamics. According to the first law of thermodynamics, you know that energy cannot be created or destroyed. It can be just converted or transferred from different bodies to each other, or from system to surrounding, or vice versa. And but if you notice, some of the process just happen in one direction. Imagine a hot coffee in a mug like what you can see in this figure. If we put if the temperature of the coffee inside this mug is 80 degrees Celsius, and if we put this mug in a room with the room temperature like 25 degrees Celsius, after a while temperature of the hot coffee inside the mug will reduce, and you know what is the reason for that? Thermal energy or heat is transferred from the hot coffee inside the mug to the surrounding, which is the room air. Then temperature of the hot coffee is reduced. So energy here is not destroyed or it is not created. It is just transfer thermal energy from hot coffee to the air inside the room. You have seen in and you have experienced this in many cases. But how about the reverse direction? Why, if we put something, if we put a mug like with this condition, with high temperature, which contain high temperature coffee inside the room, which its temperature is just room temperature, normal temperature, like 25 degrees Celsius. Why temperature of hot coffee is not increased? Why it is not increased from 80 degrees Celsius to 82 degrees Celsius? In other words, why temperature or heat is not transferred from the air to the hot coffee? If it violates the first law of thermodynamics, according to the first law of thermodynamics, energy cannot be destroyed. It can just be or created. It can just be transferred. So if even temperature of hot coffee increase due to the thermal energy transfer from the air inside the room to the hot coffee, it does not violate actually the first law of thermodynamics because energy is only transferred to the hot coffee. But this is not what we can see according to our experience. We cannot see this happen around us. We haven't seen, I think also you haven't seen such a process, increase in the temperature of hot coffee inside the room with a normal temperature. However, it does not violate the first law of thermodynamics, but it is not possible to happen. We need to consider it. We need to find another reason for that. So we have only in this direction. This process only happen in this direction. Energy actually here or thermal energy is transferred only from uh, hot coffee here, which has higher temperature compared to the temperature of the air, and temperature and this thermal energy only can transfer from a body, which is hot coffee here, to a body with lower temperature, which is air inside the room. We can only see that, and all of us have seen that like that. Another example is this one, transferring heat to a paddle wheel in the reverse direction. Generally, or normally actually, if we attach a shaft like this to a paddle wheel inside, which this paddle wheel is inside a chamber, the chamber contains air, and if we attach a weight to the shaft of this paddle wheel, and if we leave this weight to go down, this shaft will rotate, and the potential energy actually of this weight will convert it to the rotation of the shaft or kinetic energy of the shaft. Then it is transferred to these paddles. Then those paddles will cause moving of the air inside the chamber. Then kinetic energy of this paddle will convert it to the kinetic energy of the molecules of air inside the room, inside the chamber. Then temperature of the and you know that movement of the molecules of the air inside this chamber will cause increase in the temperature of the air inside the chamber. So this mechanical work actually is converted to the heat or thermal energy, which cause increase in the temperature of the air inside this chamber. We can see this process in this direction. If we just leave this weight, it will go down. This shaft will rotate, the paddle will rotate, cause disruption of the or motion of the air inside the chamber, then increase in the temperature of the of the air inside the chamber. But what about reverse direction? If we give heat to this paddle, or if we just put a candle or something here, or a heat source in, for example, here, if we give temperature to this uh, chamber, will rotate in reverse direction, and this shaft will rotate, and this weight will come up. No, we haven't seen a process like that. So this process also has a certain direction. Only it can happen uh, like what I told you. This weight can go down, rotates the shaft, then increase the temperature of the air inside this chamber. Reverse direction cannot happen. However, it does not actually violate the first law, because in this direction mechanical work is converted to the heat or thermal energy inside the chamber. It doesn't violate the first law. How about the reverse direction? It still does not violate the first law, because if we give heat here, if it this paddle will start to rotate, only thermal energy is converted to the mechanical energy. So the first law is not violated, but we cannot have that process. Again, you can see here we need another reason why we cannot have a process like this. Why, if we increase temperature of the chamber, the paddle will start not to start to rotation. The other example is about the heat, which is uh, converted from the electrical energy. If we have a electric current through this wire, according to the previous chapter, you know that the thermal energy is produced. In other words, electrical work will convert it to the thermal energy or heat. But if we give heat to this wire, we will have any current in the wire? Any current will produce in the wire? No, we don't have such a process. So the direction also for this process is only in this direction. Only if we have current in the wire, the thermal energy or heat is generated. And it does not violate the first law. Electrical work converted to the thermal energy. So it does not violate. About the opposite direction, it still does not violate the first law, because heat or thermal energy can be converted to the electrical work. But we don't have such a process. Again, we need to have another reason why we have only in this direction, why the process is only in this direction. Only if we have a current in this wire, heat is generated. We don't have any process like this. If we give heat to this wire, produce electricity. So another reason should be there, not only the first law, to have a process to determine the actually direction of the process. So process generally occurs in a certain direction, as you can see, as you have seen in previous slide, and usually mm, most of process only can happen in one direction, and the direction of a process can be determined by second law actually. After we check first law for a process, if process satisfy first law, it means that process can happen. But to determine the direction of the process, we need to check second law. So a process to happen need to satisfy both of these laws, first law and second law of thermodynamics. However, up to here, actually, I haven't defined this second law of thermodynamics. I will introduce you this second law. And as I said earlier, second law of thermodynamics is closely related to the entropy. and generally the process happen in direction which increases the entropy of the system, which entropy is topic for next chapter. So here, first let me tell you what is the major uses of second law of thermodynamics. First of all, it determines the direction of process, which is really important in many engineering applications, and from mechanical engineering to chemical engineering, because even for the chemical reaction, the second law is the law which determines the direction of the reaction actually. And also this second law shows that energy has quality. According to the first law of thermodynamics, you have learned that energy has quantity. We can measure that, and we can see, and we have actually checked that energy cannot be destroyed or created. According to the first law, which is conservation of energy, energy can only transfer. According to the uh, second law of thermodynamics, we will discuss about the quality of energy as well. The first law is about quantity, and second law helps us to discuss about quality of the process. So second law provides the necessary means to determine the quality as well as degree of degradation of energy during a process. Later, we will more discuss about this characteristic of second law of thermodynamics. Moreover, this mm, law help us to determine why a process does not happen in a direction, and how we can we can provide the condition for a process to happen in our desired direction. And also it will determine the theoretical limit for performance of commonly used engineering systems. We will see what I mean from this commonly used energy engineering system. It is like different kind of engines, like a power plant and so on. And this law actually determine why the efficiency of those kind of devices or equipment or engineering devices are limited, and why we cannot have a process or a cycle actually or a device with 100% efficiency. Later I will introduce you that. And also it determines the degree of completion of chemical reaction. And as I discussed earlier, uh, and as you know, the chemical reaction also is a process. During this process, different types of uh, substances will react, and those reactants or substances will convert it to some products. The direction of this process also depends on the first law of thermodynamics, and also it helps us to determine a chemical process how much is complete. This is also helpful when we discuss about the internal combustion engine, because as you may know, we have a chemical reaction in this type of the devices, and the fuel is reacted with the air, and how much fuel is required to have the most possible uh, energy or efficiency for internal combustion engine also can be determined by the second law of thermodynamics. Before I start to specifically discuss about the second law of thermodynamics, let me introduce some concepts which may be useful to define the second law of thermodynamics. First of all, I need to introduce you thermal energy reservoirs. Thermal energy reservoirs actually are a hypothetical body with relative large thermal energy capacity, which means their mass times specific heat is quite uh, big amount. In other words, this kind of this body or this uh, source or sink which I will introduce you, their temperature or their thermal energy actually does not change significantly if we add or if we remove a specific amount of heat from them, as you can see here. So simply these type of body are not that much sensitive to change in the temperature. A few examples of them are river, lake, and oceans, which if we add some substances with different temperature, they cannot change the temperature of the river or lake or ocean significantly. In other words, we can ignore the change in the temperature of these bodies due to the that absorption or releasing of the substance or even energy. We call them thermal energy reservoirs. And according to these absorption or releasing of energy, we divide them to the thermal energy source, which can release a specific amount of thermal energy or heat without changing in their temperature. And also we can have sink, which are the uh, uh, energy reservoirs which can absorb heat or thermal energy or a specific amount of heat or thermal energy without changing in their temperature. So if the thermal energy reservoir can release energy without changing the temperature, we have a thermal energy source. If it can absorb a specific amount of thermal energy without any changes in its temperature, we have a heat thermal energy or heat sink. As you know, we can, instead of thermal energy, we can say heat. So heat source or heat sink. This is two types of energy, thermal energy reservoirs. One of them can release, the other one can catch the energy without change in their temperature. And what is important to notice about these reservoir is they are not it is not compulsory to have a very big body or the size of body be large body to have this characteristic to be a thermal energy reservoir. Actually, it depends on the problem and it depends on the process which is happening in contact with that thermal energy reservoir. For example, if we go back to our example, if we put that hot coffee inside the room, the temperature of the air inside the room will not change significantly. So the air inside the room is a heat sink for that hot coffee mug. The other example is two phases substances or systems which the thermal energy or the thermal energy which come to the system will cause the change in the phases. More liquid, two phase, the phrase of this phrase two phase means liquid and vapor in a equilibrium condition. Its temperature is constant. If we add some thermal energy to that, these extra thermal energy will cause evaporation of more liquid, and more liquid will convert it to the vapor. But temperature of the whole system will be constant. These kind of the systems also can be a heat sink or thermal energy reservoir. The other examples, which you, as I said, are ocean, lakes, rivers, and as I said, it depends on the process which is happening and also the condition of the process. After definition of these thermal energy reservoirs, I need to introduce you heat engines, which are the basic equipment we use for energy conversion usually. According to the first law of thermodynamics, you know that energy and work can be converted to each other. If you remember this example, We can have a paddle like this. The shaft work for this paddle can be converted to the heat of the increase in the temperature or thermal energy of the water. Then work can be converted to the heat. You know that from the first law of thermodynamics. But actually, it is not that much easy to have a device to convert heat to the work. In other words, if here we add heat to the water, it does not it can it will not cause rotation of the shaft. In other words, we cannot just simply give the heat or thermal energy to the water here inside this chamber to rotate the shaft. The shaft, even we increase the temperature or thermal energy of the water inside this chamber, this shaft will not rotate. In other words, it is not that much easy to convert energy to work. We have some specific devices which we call them heat engines, which are mainly used to convert heat or thermal energy to the work. And it is not simple like what you can see here, and it has some different components like what you can see here. You can see different component of that. The component of a heat engine is like what you can see here. First of all, these heat engines can receive heat from a high temperature source, like what you can see here, like solar energy, oil furnace, nuclear reactor, and so on. Two, they have a conversion part of this heat to work, usually in the form of rotating shaft, like turbine and so on. And also they reject the remaining waste heat to a low temperature sink, like the atmosphere, river, oceans, and so on. This is like what you can see here. For these devices, heat engines, they receive high temperature. They have actually a high temperature source. Temperature will come to a mechanical part which can convert uh, heat or thermal energy to mechanical energy, which is usually the rotation of the shaft. Then the extra energy will be delivered to a low temperature sink. And during this process, we have W net out or a work generation by this device, which we call that heat engine. And what is also important to notice is these devices or equipment are operating on a cycle. In other words, these process, these happen uh, in a cycle, and it can be, and the process after the temperature release to the lower temperature thing, again another cycle start, and high temperature source give the energy to the heat engine convert energy to the work, and extra will go to the low temperature. This is just a small just a schematic diagram. Later we will see more detail about this kind of devices. And the other important thing about heat engine is this kind of devices usually contain fluid, which this fluid actually is transferring this thermal energy and can rotate a shaft or rotate a turbine. Then that rotation can be converted to the uh, shaft work. Then we can use that shaft work to uh, uh, according to our purpose. This fluid, which can transfer this thermal energy from the high temperature source to the low temperature sink, and during that heat engine can produce mechanical work, is called working fluid. In other words, heat engine and other cyclic devices usually involve a fluid to and from which heat is transferred while undergoing a cycle. This fluid is working fluid. Later, we will also in some examples what can be these working fluid. But generally, the the most common type of working fluid is water, and this is because of its specific characteristics, which we will see later. Usually in heat engine, some of the work output or W net output of the engine is being used as the input for the heat engine to keep the engine in working. So we have a efficiency of or the network output of a heat engine can be calculated by this equation or the W out which we can get from the heat engine and the required minus required work which is needed or required to continue the work of heat engine. So usually for all type of the heat engines we have this W net out or the useful work which we can get from a heat engine is equal to W out minus W in for that heat engine. But this word heat engines is a very broad word for all type of the engines, and as you may already recall that this word also include internal combustion engines and other type of the engines which we have. However, if you notice or you have seen internal combustion engine in these equipment or devices, fuel is uh, combined or reacted with the air and it will burn inside the chamber and the work and heat will release due to this reaction. And we don't have actually a cycle which liquid come to the system and go out, come to the engine and go out from the engine. And we usually consider these kind of devices in other way, and we do not define actually that working flow for this kind of devices. What in this section we are going to more focus are about a steam power plant. What I have actually introduced here is more specific for a steam power plant. A steam power plant includes four main components like what you can see here, a pump, a boiler, a turbine, and a condenser. Boiler is the heat source. As I discussed earlier in previous slide, we need a source of heat or energy to which is transferred to the working fluid. The working fluid in most of the power plant is steam or water. Then we have water here. Water due to this huge amount of the thermal energy is evaporated and we have a high temperature steam here which is under high pressure. It will come to the turbine, will cause rotation of the turbine due to its high pressure. Then turbine will rotate and it's the thermal energy of the steam actually will be converted to the uh, shaft work or to the work of the shaft of the turbine. Then this steam will go to a condenser, which is the sink actually, and the extra heat will release to the sink. And again, this process will happen. And as I said, some of the work which we have as output of the turbine will be used for rotation of the pump, which is a device to send the uh, water from condenser to the boiler. So we have such a cycle in a steam power plant, which is completely in accordance with the condition which I mentioned in previous slide for a heat engine. So a steam power plant actually is a heat engine with this characteristic. It has a working fluid, it has a heat source, sink, mechanical part which the convert the uh, heat or thermal energy to the mechanical energy. And as you notice here, we have a waste of energy. Q in will come here. It will the steam will come here. It will cause rotation of the turbine. Then some of the energy will convert it to the work, and some part of those Q in, which is absorbed by the water, is released here as Q out to the sink. So Q in will be converted to the W out and Q out, which we have definition for all of these four. We have Q in to the system, Q out from the power plant actually, W out and W in to the system. And if we select our system like what you can see here, these are input and output. We have two input and two output for our system here. Q in is amount of heat supplied to a steam in boiler from a high temperature source, which is usually a furnace. Q out is amount of heat which is rejected from steam in condenser to a low temperature sink. This thing can be atmosphere, can be a river, ocean, and so on. W out is the amount of work delivered by a steam as it expands in the turbine, as I said here in this component of the cycle. And W in is amount of work required to compress water to boiler pressure, this part. So we have W in, Q into the system, W out, Q out from our system, as you can see here. And to calculate W net out actually for such a system, we can write Q in minus Q out. So because we have Q in here, Q in will come to the turbine. Some of this Q in will be converted to the W out. Some of that will be released to surrounding. If we imagine or assume we don't have any heat loss in the pipes or any leakage of the steam in these pipes or in whole lines, this Q in will be converted. A part of that will be converted to W out, and a part of that will be converted to Q out. In other words, W net out is this Q in minus Q out. The fraction of the Q in, which is converted to the W out, can be calculated by this. W net out is Q in minus Q out. By this, we can calculate the W net out of a steam power plant actually. These steam power plant actually are the very useful devices to produce mechanical energy from heat or thermal energy. They are very common devices to produce energy. And according to what I shown to you in previous slide, you can guess that here we have energy to the system. We need to provide that energy, which can be due to the combustion of something, burning of something in a furnace, and so on. So we need to provide that energy. According to the first law of thermodynamics, you know that this energy will not be destroyed. So energy here is produced, given to the cycle, to the boiler. Some of that, with assumption no leakage, no heat waste or heat loss in the pipes or in the boiler or in the turbine, some of that will be converted to W out. Some of that will be converted to the heat, the Q out, or will release to the sink. So this amount of energy or thermal energy which is released to sink is waste of this cycle actually, because it does not it, uh, any useful work. It is just released to the surrounding, to the sink. So the useful work which we can get from this cycle is only this W out. So we can define efficiency parameter which we call that thermal efficiency, which is a ratio of net work output to the total heat input. We give Q in amount of energy to the this steam power plant, and we will produce, or we will get the W out net amount of work or useful work from the cycle. And according to what you can see here, this ratio will not be equal to 100% at all, because some of the energy should be released to the thing, and we will see why we need to have that energy waste in the cycle. But let me just discuss more about thermal efficiency. To calculate thermal efficiency, as I say, simply we can divide W net out divided by Q in, energy is given to the system, or heat which is given to the system, and W net out, the useful work which we can get from the uh, steam power plant. And this is eta TH, or thermal efficiency of the cycle. And as I said earlier, W net out is Q in minus Q out. This one, if we substitute this Q in minus Q out here, Q in minus Q out divided by Q in, then if we just simply this minus this will be 1 minus Q out divided by Q in. So we have also this equation according to the, this is according to the thermal energy which is given to the boiler, and thermal energy or heat which is released to the condenser or sink. So if we have each one of these two parameters, we can calculate thermal efficiency for our power plant. And the power plant is according to that schematic which I uh, showed you in next in previous two slides. We had something like this: source of energy, heat input, which can be, for example, 100 kilojoule, and waste of the energy to a sink or a, a condenser with lower temperature. The thermal efficiency, generally the thermal efficiency, or normal common thermal efficiency for different type of the uh, this power plant can reach only the maximum is 60%. And this thermal efficiency for such other heat engines like internal combustion engine, gasoline uh, type or diesel type is in range of 25% to only 40%. So in even in most efficient type of the power plant, we have almost one half heat loss or waste of energy to the surrounding, and it is also mentioned here. Why we need to have this waste of energy to the surrounding? First of all, just in this slide, just let me review this equation for thermal efficiency, because it is important and one of the most important, or the characteristic for a power plant or any other type of engine uh, is its thermal efficiency, which you can see here. You can calculate by this equation, even by this equation, W net out divided by QH, or simply 1 minus QL divided by QH, which is again the temperature, the high temperature reservoir, and for low temperature reservoir. So you can see different equation to calculate thermal efficiency for different type of heat engines, or for the different type of steam power plants. Why we need to have that Q out? Why we need to have that energy waste or energy releasing to the sink? Let me tell you the reason by an example. Imagine we have a piston cylinder device like this. A gas is inside the cylinder. Its temperature is 30 degrees Celsius. And the piston uh, the load also, the weight is also is placed on top of the piston. If we increase the temperature, if we give thermal energy or heat to the gas inside this cylinder, its temperature start to increase, then its pressure is increase as well. Then it will cause to the movement of this piston and the load on top of that upward. It will uh, move upward until it reaches another stop, two stops, which are the higher limit for the motion or movement of these pistons. Now, if we remove this load, uh, the temperature, if we increase temperature of this gas to 100 degrees Celsius, it will continue and it will reach to this upper limits, which are to stop. If we remove load, the temperature will reduce a little. The equilibrium temperature will be 90 degrees Celsius because some of the energy will release to the surrounding. Now, if we are going to again have this cycle, if we want to continue to have again this movement upward, we need to release some energy of this gas to surrounding, like what you can see here. Then this piston will can come and will come downward actually, and it will come to the initial state as you can see here. Then again the cycle can start. So to have a cycle like this and or anywhere, we need to have these heat energy releasing or to the sink or so on. Or we need to have these Q out. Without this Q out, this load, this piston cannot come downward or it cannot go to its initial state. We need to release energy to the surrounding. So heat engine cannot work without releasing of the energy, some fraction of the energy to the sink, and we need to have this Q out to have the this cycle continuously. Without that, it cannot happen. And why we are interested to reduce this Q out? Because if you notice here, if Q out is 0, the thermal efficiency is 1 or is 100%, which is very desirable. All of the energy is converted to the work. We have a device which we give 10 kilojoule energy, it will produce 10 kilojoule of work. And but if we remove this Q out, its efficiency will be 100%. But we need to have this Q out because of this reason, to have this cycle. Otherwise, we have only one process. Temperature is increased, the piston is will move, but the cycle cannot be restarted again. So we need to have this heat release to the sink as well. In a steam power plant, the condenser is a device with a large quantity of waste heat is rejected to rivers, lakes, or the atmosphere. And we need this, especially for a steam power plant, to reduce the temperature of the working fluid here, as you can see here. If temperature of the working fluid is not reduced here, how it can be again this process happen? In other words, we cannot again move this uh, working fluid again to the turbine. We need to release its energy to the sink. Then we can increase its pressure and send to the boiler. Then its energy again increase and turbine can work. However, as you notice here, we don't need to remove all of those energies or most of the energies. And because of that, this steam power plant have higher thermal efficiency because we don't need to release huge amount of Q out uh, to the sink. Just the fraction of the required energy to be released to the sink is lower than compared to devices like internal combustion engine, like this piston cylinder you can see here. In this piston cylinder, if you want this piston again go to its initial state, we need to remove all of that energy. Here we need to, for example, here we need to give 100 kilojoule heat to the gas to increase its temperature to 100 degrees Celsius to move this piston upward to reach this upper limit. Then if we remove the loads, the required energy to keep this piston here will reduce this much because this is the work about that, the required load for that. If we remove the load, 15 kilojoule required energy also will be removed. So only 85 kilojoule energy is enough to keep the piston here. Then if we want the piston go back to its initial state, we need to remove these 85 kilojoule energy from the gas. So you can see here that all that thermal energy will need to be released to the sea. So because of that, because this device is what we have in internal combustion engine. Because of this, Q out is big in internal combustion engine compared to the steam power plant. Because of that, the thermal efficiency of the engines or internal combustion engine is lower than a steam power plant. Then we cannot, according to this, we cannot remove this Q out because if we don't have Q out, we don't have a cycle. The cycle cannot be complete. And as I said here, energy heat engine must waste some energy by transferring to low temperature reservoir. This is very important because uh, for many years there was a question how we can reduce this Q out. And the best possible option up to now is a steam power plant which has lower value or amount of Q out, enable us to have a more efficient heat engines with efficiency about 60% or even higher in new and modern steam power plants even to 80%. Here we have some example related to what I have told you. We will see in this example how you can calculate thermal efficiency and so on for these heat engines or steam power plants. In the first example, we are going to calculate the net power production of a heat engine. This is a general example for different type of heat engine actually, because in different type of heat engines, as I discussed earlier, we have similar components. In the heat engine, in this example, we have a furnace, a river, which are required component, and also the heat engine is which convert the heat from the furnace to the useful work, and part of fraction of that useful heat from the furnace is also released to a sink, which is a river. The heat is transferred to a heat engine from a furnace at a rate of 80 megawatt. It means this is Q dot H, or the heat or thermal energy which come from the furnace to the heat engine. If the rate of waste heat rejection to a nearby river is 50 megawatt, or Q dot L to the river from heat engine is 50 megawatt, we need to determine the net power output, or W dot out net, this one, And also we need to determine the thermal efficiency for this heat engine. How much is thermal efficiency of this heat engine? According to this schematic, actually, everything will be much easier. First of all, we need to assume that we don't have any heat loss in the pipes and mm, different components of our heat engine. Then this Q dot H will be only converted to the Q dot L plus W dot net out. And according to the what you have learned in previous slide, W dot net for such a heat engine will be equal to Q dot H minus Q dot L, or the difference between the energy which is given to the heat engine minus and energy which is released to the sink, which is river here. So Q dot H minus Q dot L, Q dot H is 80 megawatt, Q dot L is 50 megawatt. Simply we can calculate the W net out of this heat engine, or the net power output of this heat engine is 30 megawatt. To calculate thermal efficiency, simply we can use this equation as I introduced this equation. W net out is the useful power which we can get from the heat engine divided by the uh, heat or the thermal energy rate here, which is given to the heat engine. 30 megawatt divided by 80 megawatt will be 0.375, or multiplied by 100 equal to 37.5%. In other words, thermal efficiency of this heat engine is 37.5%. And if you notice here, because this equation was like this, W net divided by QH. But because both of them are in rate form, it's okay. We can again, because this means power work per time, and this is Q dot H, heat transfer per time, or thermal energy transfer to the uh, heat engine per time. So both of them are per time, so we can have this division like this. So thermal efficiency is 37.5%. In other words, only 37.5% of the energy or thermal energy which uh, come to the heat engine from the furnace is converted to the useful work, and rest is delivered or released to the river as a waste, or waste heat loss, or waste of energy to the river. So only we can get 37.5% useful work from this heat engine. The other example is about fuel consumption rate of a car. As you know, in car we have internal combustion engine. Internal combustion engine also is a heat engine. However, the structure is different from the power plant, the steam power plant especially, but the component, the schematic can be like this. It has a combustion chamber, which is the heat source, and atmosphere is the sink. And car engine is our heat engine here actually. And for an idealized car engine, actually, it means we don't have any heat loss to the surrounding. However, we have this actually. We have different reasons for heat loss, but and also waste of energy due to friction and so on. But we can assume that the energy, thermal energy, which is produced due to the combustion, is converted only to the useful work and the shaft, which go to the wheels, and also the heat or thermal energy which is given to the atmosphere by exhaust tailpipe or the other temperature uh, heat transfer from the body of the engine. So Q dot H equal to W net out plus Q dot L. Q dot H is converted to W dot N plus Q dot L. This car engine with a power output of 65 HP. So W dot net output of the engine is 65 HP. Has a thermal efficiency of 24%. 24% or 0.24. We need to determine the fuel consumption rate of this car if the fuel has a heating value of 19,000 BTU per pound. In other words, each pound of this fuel, if we burn it, will produce 90,000 BTU energy. So we need to find mdot of fuel or rate of fuel consumption by this engine produce this much of power output actually, and we know the heating value of the fuel as and also its thermal efficiency. Simply, we according to this schematic also we know that Q dot H or thermal efficiency again because it is a heat engine will be W net out divided by Q dot H. Simply by restructuring, we can have this Q dot H equal to W dot net divided by thermal efficiency or exactly H. We have W dot net out, which is 65 HP. Thermal efficiency also is 0.24. And we need to use this unity conversion ratio. 1 HP is equal to 2545 BTU per hour. This is unity conversion. To cancel HP, then unit will be BTU per hour. By calculation, this calculation 65 times 2545 divided by 0.24 will give us this amount of required heat transfer to this car engine to have this thermal efficiency. Okay, so we know how much energy we require for this engine. Then, because we know the energy and we know how much energy is released by burning of 1 pound of the fuel, simply if we divide the required energy, this is required energy to the energy released for each pound of fuel, then it will give us the required mass flow rate of the fuel to have this efficiency for this car engine actually, which is 36.3 pound per hour. This is required mass flow rate for this car engine. So if we divided Q dot H or required rate of heat source or heat energy to the heat engine to the possible heat which we can get from each pound of the fuel, then we can calculate the mass flow rate of the required mass flow rate for this engine. And if you notice here, if thermal efficiency was double actually, then the required fuel will be half compared to this. In other words, if this thermal efficiency is 48% or 0.48, it means the fuel consumption will be half of this, or and you can see here how much is effective thermal efficiency on the fuel consumption. And this is the reason we are interested to increase the thermal efficiency of these kind of devices, because it will help us to reduce the fuel consumption and reduce costs for example, car engine. So higher thermal efficiency is desirable due to the economy, due to the cost, and also later or in previous chapters also you have seen that to reduce the air pollution as well by reducing the